Welcome to our deep dive into the world of logic gates, the fundamental components of digital circuits. These little guys are the building blocks of everything from the simplest calculators to the most powerful supercomputers. Yep, that's right. All the magic your phone or laptop does can be boiled down to these tiny logic gates working together in incredibly complex ways. Now you might be thinking, logic gates? Sounds boring, but trust me on this one, it's way cooler than it sounds. Imagine a system where you only have two options, yes or no, on or off, 1 or 0. That's the world logic gates live in. And by combining them in different ways, we can create circuits that make decisions, perform calculations, and control the flow of information. In this video, we're going to demystify logic gates and show you how they work. We'll cover the basics like AND, OR, and NOT gates, and then we'll move on to some slightly more complex gates like XOR, XNOR, and NAND. So buckle up, smash that like button for the algorithm, and let's jump right in. Alright, first up we've got the AND gate, the gatekeeper of the logic gate world. Think of it like a bouncer at a club. The AND gate only lets the party through if inputs are true or high, represented by a 1. In the real world, this could be two buttons being pressed simultaneously. If both are pressed, input 1 and input 2 are high, the output is 1, meaning the action can happen. Now let's say only one button is pressed, or maybe even none at all. In the AND gate's eyes, that's a no-go. If either input is 0 or low, the output will also be 0, no matter what. This is where the truth table comes in handy. It's basically a cheat sheet that shows you all the possible input combinations and their corresponding outputs for a logic gate. For the AND gate, the truth table clearly shows that the output is only 1 when both inputs are 1. Otherwise, it's a big fat 0. Simple, right? But don't let its simplicity fool you. The AND gate is essential in countless digital circuits, acting as a critical decision maker. Next up, we've got the OR gate, the inclusive friend of the group. Unlike the AND gate, which needs all inputs to be true, the OR gate is happy as long as at least input is true. Think of it like this. You want to turn on a light and you have two light switches connected to it. If either switch is flipped on, the light turns on. It doesn't matter if both are flipped or just one. As long as there's at least one input, the output is a go. The OR gate follows the same logic. If either input is 1, or even if both are 1, the output will be 1. The only time the output is 0 is when inputs are 0. Again, the truth table makes this crystal clear, showing all the possible input combinations and their corresponding outputs. The OR gate is super useful in situations where you want an action to happen if of multiple conditions are met. For example, in a car alarm system, the alarm might be triggered if the door is opened or if the motion sensor detects movement. Now let's talk about the NOT gate, the rebel of the group. This gate is a bit of a loner, only dealing with one input at a time, but what it lacks in inputs, it makes up for in attitude. The NOT gate is an inverter. Whatever you input, it'll spit out the opposite. Feed it a 1 and it'll give you a 0. Give it a 0 and it'll throw back a 1. Think of it like a light switch with its wiring reversed. Flipping the switch up turns the light off, and flipping it down turns it on. That's the NOT gate in a nutshell. It takes an input and flips it to its opposite state. The truth table for the NOT gate is pretty straightforward, since there are only two possibilities. Input 1, output 0, input 0, output 1. Despite its simplicity, the NOT gate plays a crucial role in digital circuits, often used to invert signals or create logical negations. Chapter 4, XOR gate, the exclusive one. Now things are about to get a little more interesting as we move into the realm of more complex logic gates. Let's talk about the XOR gate, also known as the exclusive OR gate. This gate is a bit pickier than the regular OR gate. It only outputs a 1 if of its inputs is 1. If both inputs are the same, whether they're both 1 or both 0, the output will be a resounding 0. Imagine you have two people voting on something, but only one vote counts. If they both vote yes or both vote no, the vote is null and void. The XOR gate operates on the same principle. It's looking for that one decisive input, that one vote that tips the scales. The XOR gate is particularly useful in applications like error detection and data encryption, where you need to identify discrepancies or create unique combinations. Chapter 5, XNOR gate, the XOR's opposite twin. Next we have the XNOR gate, which, as you might have guessed, is the XOR gate's opposite twin. Remember how the XOR gate only liked it when its inputs were different? Well, the XNOR gate is the complete opposite. It loves it when its inputs are the same. If both inputs are 1, the XNOR gate gives you a 1. If both inputs are 0, it still gives you a 1. It's only when the inputs are different, one being 1 and the other 0, that the XNOR gate throws a tantrum and outputs a 0. Think of it like this. You and a friend are deciding what to eat. You both want pizza. Great. You both want pasta. Fantastic. But if you want pizza and your friend wants pasta, well, now you've got a problem. That's the XNOR gate in action. The XNOR gate is often used in applications like parity checking, where you need to ensure that data has been transmitted correctly. Chapter 6, NAND gate, the universal builder. Last but not least, we have the NAND gate, the MacGyver of the logic gate world. This gate is special because it's considered a universal gate, meaning you can build any other logic gate using just a combination of NAND gates. Talk about versatility. But what exactly does it do? Well, the NAND gate is basically an AND gate with a rebellious streak. It takes the output of an AND gate and flips it thanks to that little circle which represents the NOT gate at the end. So, if both inputs are 1, the NAND gate outputs a 0, and if any input is 0, the output is a 1. The NAND gate's claim to fame is its universality. You can create AND, Oregon, NOT, any gate you can think of just by wiring a bunch of NAND gates together in different ways. It's the ultimate building block for digital circuits. And there you have it. We've explored the fascinating world of logic gates, from the simple AND and OR gates to the more complex XOR, XNOR, and the incredibly versatile NAND gate. Remember, these gates are the fundamental building blocks of all digital circuits, working tirelessly behind the scenes to power our computers, smartphones, and countless other electronic devices. Hopefully, this video has shed some light on the mysterious world of logic gates. It's amazing to think that such simple concepts can lead to the creation of incredibly complex and powerful technology. Thanks for watching. Don't forget to like, subscribe, and hit the bell icon for more tech insights. Until next time, keep those circuits firing.